Hi everybody. I am Sivanathan, the first and corresponding author. Second author is Dr. B.K. Vinayagam. The third and fourth authors are Mr. Tanmay Samak and Mr. Chinmay Samak respectively. We are from SRM Institute of Science and Technology. The title of our paper is Decentralized Motion Planning for Multi-Robot Navigation Using Deep Reinforcement Learning. We have organized our presentation under four major sections. First, motivation. Second, problem formulation and preliminaries. Third, implementation aspects. And fourth, results and discussions. Now, Dr. B.K. Vinayagam will present the first section, that is the motivation for this work.
Online motion planning for a group of robots is a fundamental challenge to overcome in order to successfully implement the following applications: search and rescue missions, collaborative material transfer, warehouse management, connected autonomous vehicles, even aesthetic performances. Although this problem has been explored in the recent past, the existing solutions need further improvement. In general, the multi-robot motion planning can be implemented in two ways: centralized and decentralized. Centralized methods use a central server to plan the trajectories for all the robots. Therefore, the generated trajectories are usually safe, optimal, complete. However, the centralized methods are not suitable for highly dynamic environment, especially when scalability and robustness is desired. On the other hand, in decentralized methods, every robot plans its own trajectory by using its own onboard resources. Hence, these are naturally robust and scalable, but generated trajectories are relatively suboptimal and unsafe. Thus, our work focuses on decentralized planning. Many solutions have been proposed for the decentralized multi-robot motion planning so far. They can be broadly grouped under two categories: classical optimization based approaches and learning based approaches. Classical optimization based approaches may be further categorized as constraint and unconstrained optimizations. Theoretically, the constraint optimization methods provide safety guarantee but take longer travel time and become computationally intensive in higher dimensions. But unconstrained optimization methods use their soft constraints or no constraints. So they tend to be faster in execution and shorter travel time but less safe. Nonetheless, classical optimization based methods do not provide safety guarantee in practice owing to the fact that multi-robot motion planning is a rather complex problem demanding highly non-linear models to be solved in real time with persistent model and measurement uncertainties. Thus, the learning-based methods address this issue by making use of artificial neural networks as nonlinear function approximators, which inherently learn to cope with uncertainties and enable real-time execution in the inference stage. Deep limitation learning methods are well suited for single agent systems such as autonomous vehicles but are seldom applied directly to multi-agent systems owing to labeled data requirements of permutative and complex interactions. Deep reinforcement learning methods alleviate this problem by learning through self-exploration. Thus, we used deep reinforcement learning in this work. So overall consolidated problem statement is we have to develop a multi-robot trajectory planning method that could generate trajectories on the move in decentralized manner, ensuring scalability and robustness with continuous time representations for smooth transitions, with faster transition time while mitigating inter-robot collisions with least communication dependency. Now Mr. Sivanathan, Assistant Professor, will explain the second section.
Unlike classical optimization methods, in a data-driven approach like reinforcement learning, any dynamic system or process can be modeled as a Markov decision process in general, in which the next state of the system is decided only by the current state and the action taken. Similarly, the decentralized multi-robot motion planning can also be modeled as a partially observable Markov decision process of 7 tuple, where S is the state space, capital A is the action space, capital T is the conditional state transition probability that action A in state S at time t will lead to state S hat at time t plus 1, where S at is the new state which has resulted, and R is capital R of S comma A is the expected immediate reward an agent has received after taking an action A in the current state S and transitioning to a new state S at. Capital Omega is the observation space. Capital O is the conditional observation probability of receiving an observation after transitioning to new state due to an action A. Gamma is the discount factor, which usually lies between 0 and 1, which motivates the agent to either favor immediate expected reward or cumulative reward over future horizon. So therefore, the objective of the partially observable Markov decision process, or the objective of this problem, is to find a policy or an optimal policy pi that makes the agent to choose an action A which is equal to pi of S when in state S. I've been referring thus for agent. So agent is nothing but an intelligent entity, and in fact which is a software sitting in the actor, and is capable of making observations and taking decisions, and above all it could learn. So the partially observable Markov decision process now reduces the probability distribution as a Markov transition matrix, and the resulting combination behaves simply like a Markov chain, which I have already discussed. Yes, the process that I have been explaining so far is illustrated in the schematic, wherein the chessboard like structure is an environment which is in fine grid form, and the blurry colored objects that you can see on the environment are agents or the robots, which are also shown in the rectangular box in order to show how the robots interact with the environment and their relationships, and also you can see the policy optimization. So the entire schematic is presented here to show how these three entities interact with one another. Basically at each time step t, every ith agent gets an observation O sub t and a reward R sub t, and performs an action A sub t based on the policy pi that it has learned so far. So based on this new action, the robot or the agent will eventually get into a next state at time instant t plus 1, and this can be observed as O sub t plus 1, and also the environment returns the reward for the new action that it has taken, which is R sub t plus 1, and using this information and also the policy that it has learned so far, it will produce an action at time t plus 1 again. Now let me add little more details about state space, observation space and action space. The state space here is partially observable and partially hidden. The observable states are the own positions, and the goal positions are hidden states. So the state vector of an individual agent can be expressed as in the equation 1, where S superscript O is the observable positions, and S superscript H is the hidden states, which are nothing but the goal coordinates, which are defined in a two-dimensional vector space. Considering the n agents and partially observable state space, the observable space can be given in the equation 2. At each time step t, every ith agent collects a vectorized observation where p superscript I is the position of an ith agent in xz plane. Of course, here instead of xy we use xz because the unity uses a right-handed coordinate system wherein y-axis points upwards, and g superscript I is the goal location of an ith agent relative to itself, and p tilde superscript I indicates the position of every other agent j relative to the ith agent. Before I could discuss about action space, let me make clear distinction between actor, agents, and robots. So actors are basically a physically present entity within the environment, which are otherwise the robots. So in this context, we use actors, robots interchangeably. However, as I already mentioned, the agents are the intelligent learning softwares, we could say, that control the actor or robots. So in our work, we used differential drive robots as actors, which are of non-holonomic type. Also, we considered the action space as a continuous space in order to imitate the real-world actuation, and the continuous space action vector for every ith agent comprised of its linear velocity v along local z-axis and angular velocity omega about local y-axis is presented in the equation 3. And also, in order to model the saturation limits on the control actions for linear velocity is made to confine within the limits of 0 and 0.05, and angular velocity is between -pi to +pi. Next comes reward function. In fact, reward function is one of the critical aspects in reinforcement learning, because the way how it is defined will decide the success of the implementation. So we have carefully crafted the reward function keeping in mind the goals that we wanted to achieve. So from the equation 4 you can see that the reward function gives a reward of +20 for every agent that reaches the goal successfully, and also it provides a penalty of -20 for every agent that collides with other agents or with the walls. And the third component is also a penalty where it penalizes the agent continuously or at every time step with a penalty proportional to the square of the distance from the goal. Actually, this helped us to force the agents to temporarily optimize their trajectories. Also, this has helped us to accelerate the learning process where the agents were tempted to move to the goals without getting penalized every so often. Having equipped with the problem formulation and the preliminaries, now let's explore how the multi-robot motion optimization is done in the reinforcement learning. In order to explain this, let me call upon Samak brothers to take this session forward.
The task of motion planning for n robots can be empirically formulated as an optimization problem aimed at minimizing the expected mean time to goal Tg using a policy pi defined by the parameters theta. The constraints 6 to 8 essentially define a go-to-goal behavior with both static and dynamic collision avoidance. 6 is the kinematic constraint governing the state transition from t-1th instant to tth instant in a time step of delta t due to action A. 7 is the collision constraint strictly restricting the collision of the ego robot I of radius rho with any of its peers j also of radius rho and or the bounding walls of the environment of width w. Finally, 8 is the goal constraint requiring the ith robot to reach its goal gi at the time instant tg. In the context of reinforcement learning, these constraints are handled using the reward function described earlier, which guides the agents towards optimal behavior. The objective is therefore to learn a policy pi which maps states of each robot to appropriate action A so as to maximize the expected future discounted reward. The time minimization problem defined earlier can now be redefined in terms of reward maximization problem as shown here.
In this work, we present the MARL Simulator, a custom simulator developed atop the Unity game engine and linked with ML Agents toolkit to train and test multi-agent reinforcement learning behaviors. This simulator is developed with a vision to enable rapid development and testing of deep reinforcement learning-based algorithms aimed at perception, planning, and control of multi-robot systems. The fact that this simulation system exploits Unity Editor at its core makes it much more flexible and modular to work with than any other existing standalone simulators available for such applications. Particularly, this work utilizes the MARL simulator to train, deploy and analyze multi-robot motion planning and navigation problem in the context of 4 non-holonomic robots of 0.25 meter radius within a 10 x 10 meter arena defined by the walls of 0.1 meter width. The goal location for each robot was fixed at one of the 4 corners of the square arena, identifiable by the corner pole of respective color, and it was ensured at all times that the robots were spawned only in the non-adjacent quadrants with respect to their goal locations. We first adopted the individual policy approach, wherein all agents had the same training configuration. However, each agent was assigned an independent behavior which forced its policy to be updated solely based on its own experience. We then compared the earlier models with the ones trained using the common policy approach. Here, all agents had the same training configuration and common behavior. A clone of this common policy was attached to each agent, thereby allowing the policy to be updated parallelly based on the experiences of all the agents. A total of 3 experiments were framed in the order of increasing complexity to train and deploy the behavior models. The key difference between the 3 settings being initial pose of the robots as illustrated in the figure. While the first behavior was trained using both individual and common policy approach, the latter were trained using common policy approach alone, as it was proven to converge faster while yielding similar results. The go-to-goal with collision avoidance or G2GCA experiment involved spawning of the robots at the centers of the environmental boundaries 1 meter distant from the respective wall facing towards the center of the environment. The robots had to drive safely towards their goals, which were located at diagonally right corners with respect to each robot. Next, the antipodal exchange or APE experiment required the robots to be spawned at the corners of the environment 1 meter distant from the adjacent walls facing towards the center of the environment. They had to drive to their goal locations, which were located at diagonally opposite corners with respect to each robot, without colliding with each other or the walls. Note that spawn location of one robot was the goal location for the other, which made this task even challenging. Finally, the G2GCA with random initialization or G2GCA-RI experiment spawned the robots randomly within diagonally opposite quadrants with respect to their goal locations from where they had to drive towards their goals without colliding with each other or the walls. This behavior was exceptionally challenging as the robots had to cope up with the extremely stochastic environment. We made use of proximal policy optimization algorithm to train the policies for all the experiments. A fully connected neural network with input dimensions equal to the observation vector of 10 elements, output dimensions equal to the action vector of 2 elements, and 128 neural units in each of the hidden layers was adopted as a function approximator. Needless to say, the policy parameters were simply the weights and biases of the neural network. The table here describes training configurations adopted for all the experiments. It is interesting to note that deeper neural networks induced higher nonlinearity to the trajectories. The training results comprise of cumulative reward, episode length, and policy entropy plotted against the training steps for all the experiments. A general indication of good training is that the cumulative reward is maximized and then saturated, the episode length is adequate. Now, while longer duration implies agents wandering off in the environment, very short duration may be an indicative of agents colliding with nearby obstacles. Finally, the policy entropy, that is the randomness, should decrease steadily as the training progresses. This work was particularly focused on testing the robustness of the trained models towards the stochastic nature of the environment. The trained agents were therefore tested for their performance in highly stochastic scenarios. Table here holds the success rates for all the experiments. These values are based on 500 random episodes wherein the agents were initially spawned collectively, but the respawning after each episode was left independent to each agent so as to create a highly stochastic setting. The lower success rate of G2GCA-RI behavior is justifiable in terms of 2 possible reasons. Firstly, due to the insufficient generalization of the neural network policy to the highly randomized setting, and secondly, due to the unjust inter-agent collision resulting from the agents spawning too close to one another. We also analyzed the trajectories of all the agents along with their motion control commands in order to infer the efficiency of motion planning. For the G2GCA behavior with individual policy approach, it can be observed that all the agents followed similar trajectory profiles. However, their strategies for trajectory optimization were not the same. While red and blue agents chose to maximize their linear velocities for achieving temporal optimization, green and magenta agents smartly traveled less distance at moderately high speeds to achieve similar time to goal. Furthermore, the variations in velocity profiles also indicate the cautious motion planning in closer proximity of peer agents. In case of the same experiment with common policy approach, the agents were observed to take quite different trajectory profiles as compared to the individual policy approach. Results indicate that the agents preferred to follow concave trajectories as opposed to convex ones, with higher smoothness and lower nonlinearity. The motion analysis results for antipodal exchange scenario primarily revealed that diagonally opposite agents had learned to optimize their trajectories in a similar fashion.
While red and blue agents started with a moderate velocity, slowed down a bit and then accelerated to maximum velocity, green and magenta agents did the exact opposite by starting fast and then slowing down when proximal to the goal location. This is quite an intelligent strategy to reduce the probability of collision with peer agents, yet optimizing time to goal. It is to be noted that in certain situations the agents preferred taking a slightly longer route to avoid collision with peer agents, but covered up the increased distance with a higher velocity so as to avoid increasing time to goal. Finally, a sample episode from the G2GCARI setting depicts each agent having a different distance to goal, owing to the fact that all agents were spawned at random locations with random orientations. A particularly impressive observation here is that since the red and green agents were spawned quite close, the red agent proceeded quickly with high velocity, while the green agent accelerated cautiously with a lower velocity to avoid colliding with the red agent. It later increased its velocity to reach the goal location quickly. This work was aimed at training a group of non-holonomic robots to navigate to their goals while optimizing their trajectories both spatially and temporally. While spatial optimization was concerned with collision avoidance, temporal optimization was concerned with minimizing the time to goal. A total of 3 experiments were carried out to investigate the task of coordinated motion planning for 4 cooperative robots. Initially, the common and individual policy learning approaches were compared in the G2GCA experiment, and the faster converging common policy approach was followed for the later experiments, namely APE and G2GCARI. The agents were successfully able to learn the task of decentralized motion planning in an end-to-end manner by making use of the limited observations. This work shall be pursued further to investigate the navigation problem of multiple non-cooperative agents using exteroceptive sensing modalities. With this, we conclude our presentation. Thank you for your time.